everybody, and welcome to the last video considering chapter 3, which focuses on rational functions. Today we'll be actually covering chapter 3.4 and a really tiny bit of 3.5 for reasons you will see in a little bit. Okay, so chapter 3.4 revolves around solving rational equations and inequalities. So first we're going to learn how to actually solve rational equations algebraically, then the exact same types of equations but using technology. Then we will talk about how to solve rational inequalities, and lastly we're going to talk a little bit about chapter 3.5. So let's get started. To solve an equation algebraically, you will have to follow the main objective, which is of course to get rid of the fractions. Nobody likes working with fractions, and for that reason we just try to get rid of them. So to do that, we must multiply both sides of your equation by the lowest common denominator, or the LCD. The LCD could be found by factoring each of the denominators, and the product of all non-repeating factors in the different fractions you have will be the LCD. So that might sound a little bit confusing, but as you can see I have an example at the bottom, so I'll explain a little bit further. So once you multiply all the sides by the LCD, you'll be left with some sort of polynomial equation. With that, when you're multiplying, it's the easiest thing for me to do is just simply writing the factor that wasn't in the denominator but is in the LCD into the numerator, because essentially what you're doing is just canceling out all the factors that were in the denominator for all the factors that were in the denominator. Thus, this just makes your life a lot more easier. So after you do that, all you have to do is again expand and simplify, because you'll be actually left with the factored form of a polynomial equation, and you don't want that when you're trying to group things. So again, expand and simplify, then rearrange the equation to group the variables that you know go together, isolate the variable you're trying to solve for, and again, solve. For example, let's solve the following equation. X plus 3 divided by x squared minus 15x minus 16 is equals to 6x plus 2 divided by x squared plus 2x plus 1. This will probably be one of the more difficult, or the most difficult equations you will deal with, just because it is dealing with really high degree functions. Like usually you would see like 1 over x plus 3, but I just want to show you a difficult question so you could get the hang of it, because everything else that's easier will actually be more easy to do. Wow, it's surprising, right? Okay, so let's follow the steps I outlined. So first, just factor the denominators. So x squared minus 15x minus 16 could be factored into x minus 16 times x plus 1. X squared plus 2x plus 1 could be factored into x plus 1 squared. Now we need to find the LCD. The LCD, as I said, would be the product of the all non-repeating factors in the different fractions. So our first fraction is this. So we have x minus 16 and x plus 1. Okay, we kept that. What does this have? This has x plus 1 squared, right? So the factor that is repeating is x plus 1, but it is repeated twice. Hence, we have to include it 2 times for it to make sense. X minus 16 is only included once here, not in here. That's why it's not repeating. Therefore, we have to include it. Now, let's multiply both the sides by the LCD. So what we would get is we would multiply this by x minus 16 times x plus 1. So when we do that, what we actually get rid of is x minus 16 and x plus 1, and we're left with x plus 1. That is why we actually get x plus 3 times x plus 1 in the numerator, and the denominator now equals 1, so we don't even need to write it. Now for the second part, what we're doing is again multiplying by the same LCD. We get 6x plus 2 divided by x plus 1 squared times x minus 16 times x plus 1 squared. Of both the numerator and the denominator, they cancel out, And what we get is, again, x squared plus 2, or 6x plus 2, x minus 16. So we're good there. Next, we need to expand and simplify. So let's expand this. We get x squared plus 4x plus 3. Then expanding this, we get 6x squared minus 94x minus 3. I didn't show the actual expanding steps because I'm pretty sure you know how to do it after taking grade 10 math. Now, what I want to do is rearrange the equation so we leave a 0 on one side. That just makes our life a whole lot easier. And what we get is negative 5x squared plus 98x plus 35. Now, since this is a quadratic, and we're dealing with pretty big numbers over here, I would just recommend using the quadratic formula. I don't think, considering these are the values we got, it could be factored, so that's your only option. So when we plug these values into the quadratic formula, we get the following. X is equals to negative 0.351, or x is equals to 19.951. So those are our answers for when this equation, this expression equals that expression. That's the steps you have to take. Now, when we're talking about solving rational equations using technology, what we're actually talking about is solving those rational equations that can't be factored. So over here, when we got to actually factor in the denominator, sometimes that's impossible, as we talked about, for example, in the chapter 2. But also, for example, when we got to our equation over here, we were luckily able to apply the quadratic formula. But let's say if we had a third degree function, then there's a big possibility you can't just apply a formula to it, or the formula would be really, really ugly because there is a formula. But yeah, what you would do then is actually use tech. The way you could do this is either find the polynomial function, that is, if you were able to factor in the first place, like the first equations, and turn it into a polynomial, but the polynomial you got can't be factored, then you have to just simply graph that polynomial and find its zeros using like a graphing calculator or Desmos. You could also simply just graph both the rational functions. So for example, you graph your first function, then you graph your second function, and then you just see where do the two intersect. That is also a really easy way to do it. However, your teachers might not want you to do it since it's really, really easy. But again, this way you could solve any function. For that reason, again, if you have a graphic calculator, you're most likely not going to be allowed to use it on any math evaluations just because you could solve any equation using it. And that doesn't test any of your thinking, as simply you're plugging in numbers into a calculator. Now for our third topic for today, we're talking about solving rational inequalities. So if you remember anything about inequalities of polynomial functions, you should be more than set for solving inequalities of rational functions. So let's see, what steps do we have to take? We have to factor our inequality. We write the inequality so you have a 0 on one side. Okay, that sounds familiar. Now, this is the really, really, really important part. You have to state your restrictions. Because if you don't state your restrictions, you can easily forget what x values cannot exist or cannot be part of the function. So for example, if you had 1 over x plus 1, we know that x cannot equal to -1, and we must state that. Next, you would find the lowest common denominator and rewrite the inequality without any fractions. So what we actually do over here is actually go back to the steps we just discussed when solving a rational equation. And what you'll see is everything else is exactly the same until we get to the last point, which is using an interval chart to find the solutions. Again, if you remember chapter 2.6, then this shouldn't be surprising to you, because all you'll be doing is plotting in the factors you found and then finding the intervals for x where it satisfies your inequality. So yeah, that's what I'm explaining here. Again, I will show an example just so it makes sense to you. So this example will show you how to solve one of the more difficult rational inequalities. what you'll notice in class is you might be given like a quadratic over a quadratic, and then like greater or equal to 0. You might notice something of this form. I don't recall there being anything above a quadratic, as again, chapters 3.1 and 3.2 only focus on quadratic and linear reciprocals. For that reason, this I would say is one of the more difficult ones. So let's do this question together. Okay, so let's solve this question. First of all, I'm gonna rewrite it so what we get is a proper format of this inequality. So we have x plus 1 over x minus 2, x plus 7 over x plus 1. Okay, so first step was to factor. We already have this equation factored, so it isn't a big deal. We don't have to do anything. Now we should rewrite it so that we have a 0 on one side. So I'm gonna take this to the other side, and we get x plus 1 over x minus 2 minus x plus 7, x plus 1 is smaller than 0. Now we need to find or state our restrictions. I'm gonna write our restrictions here. X cannot equal to 2 and x cannot equal to -1. Your teacher might require you to show the steps, but again, we're just making this equal 0 and then solving for what x is. Same on that side. Now, with the restrictions out the way, our lowest common denominator, so LCD, would be x minus 2 times x plus 1. With our newfound lowest common denominator, we should rewrite this inequality. So what we know is that we need to make the denominator equal to the lowest common denominator, right? To do that for the first function, or the first fraction, should I say, what you're doing is you're multiplying everything by x plus 1, which was missing before. And then to make the second one have the lowest common denominator of x minus 2, you're multiplying everything by x minus 2. Sorry, I wrote this wrong. There you go, times x minus 2, x minus 2. And then still is smaller or equals to 0. Remember, these values just equal to 1, so we're not actually changing what the function equals to. Now, with that, what we actually get is x plus 1 squared minus x plus 7, x minus 2, over, since we have the same lowest common denominator, and all the denominators are now the same, x minus 2, x plus 1 is smaller than 0. So over here, this is very important to remember. We have to keep it. Now let's expand the top. For the top, what we get is x squared plus 2x plus 1, and then minus x squared plus 5x minus 14 all over x minus 2, x plus 1. The reason why I'm not expanding this is because we need to keep this form fully factored, right? To make our interval chart. So to fully factor the top, we have to expand it first, but we don't need to expand anything at the bottom because it's already been factored. So again, smaller or equal to 0. Now we could just rewrite this as x. X gets cancelled out, sorry, because x squared minus x is 0. 2x minus 5x is negative 3x. And then 1 minus negative 14 is plus 15 over x minus 2, x plus 1. I know we're kind of got off the screen, but don't worry, I'll be coming back shortly. So, with our newfound equation, we should make an interval chart. So our intervals over here, we know that this could be further written down to, for example, negative 3x minus 5 over x minus 2, x plus 1. Remember that they should be going like vertically in a column instead of a row. Most teachers are picky about that, so don't make this kind of format on your test. Actually go downwards. Now from here, we need to make our interval chart. We have one more. Now over here we write our actual intervals, so we know x is 5 over here, 2 and -1. So our lowest value is -1. So we go from negative infinity to -1, from -1 to 2, from 2 to 5, and then from 5 to infinity. And this is not needed. Now we write down all the factors that we have. First of all, I like to write the -3 down. You could write -3x minus 5, but this is just personally my favorite way to do it. Then I'd write them in order of increasing values, so x plus 1, x minus 2, and then x minus 5. Again, over here, this is our function. I would say, for example, let f of x equal to this. So yeah, let's write that f of x is equals to -3x minus 5 over x minus 2, x plus 1. Again, don't do this horizontally. Now we just plug in the values. -3 will always be negative no matter how you change x, because it doesn't have an x variable. For x plus 1, it'll be negative over here, but positive for everything else. It'll be negative over here and positive for everything else. And then negative, 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 positive. The reason why I like writing things like this is because actually it helps you visualize the pattern a lot better. So you have 3 pluses, 2 pluses, 1 plus. It's a nice little like triangle. So now, since we have 4 minuses, this is actually a plus, 3 minuses and a plus, that's a minus, 2 pluses, 2 minuses, that's a plus, 3 pluses and a minus, that's a minus. So since we were looking for something that is smaller than 0, our answer would be from -1 to 2 and from 5 to infinity. However, I want to introduce a really important concept to you. So for example, if we had this as our original question, what we would have to do is then you would have to label where your x values cannot possibly happen. So for example, here we know it was a vertical asymptote, this was a vertical asymptote, and this was a 0, because that's what we got over here. Since we know that we can't have a value equal to the vertical asymptote, when we're writing the question for when f of x is greater or smaller than or equal to 0, we would write from the answer as when it is from -1 to x, we can't include that value, to 2, or when x is greater or equal to 5. Greater or equal to 5. So notice how this has an equal sign. Well, these both don't, because this was a vertical asymptote and our x values are restricted, therefore they cannot equal to those values. So overall, this is the solution. You should probably write it a little bit better, like actually stating when for x plus 1 to be greater than this, the x values must be in the following manner, blah 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 blah. But yeah, this is your overall solution. If you wanted to check out this question on Desmos or actually graph it, because that's possible too, I graphed the actual question first, and this is what we got. You could zoom in here and get that it's from -1 to 2 and from 5 to infinity. So we're good in that regard. Now what I want to also show is that a greater or equal to difference. Again, we see that there's no like thick line on 2 and 1 because that's restricted, or 2 and -1, but there's now a thick line on 5. Again, this is just illustrating our solution. I just wrote down what the numerator would equal to once you perform the operations of multiplying by the lowest common denominator and the missing factor. Then I simplified it down into this. Again, the equation is always the same. Like you see, there's no difference here. So this gave us the 5 as our intercept. Then you just made the interval chart and you got these intervals. So that is the solution. You could see that we did it right. Yeah, that's it for this question. With that out the way, what we have left is chapter 3.5, which focuses on making connections with rational functions and equations. So essentially chapter 3.5 is a whole chapter dedicated to the application of chapters you've learned throughout like to the concepts you learned throughout chapter 3. So it's just word problems with rational functions at its core. You'll be asked to sketch graphs, solve for certain unknowns, or analyze how tweaking certain values in the function will actually affect its outcome. However, again, since this is entirely an application question or an application section, I should say, I will not be going and making a whole nother presentation for it because it covers no new concepts. It's just testing your understanding of the concepts we have already learned. So for that reason, if you really want to know what tips I would give for you, I'd recommend just looking at chapter 2.3 presentation because it was kind of the same. It was actually testing your knowledge on the remainder theorem and stuff like that. But overall, it shouldn't be anything difficult. It might be a little bit annoying to read some word problems and then have to work with rational functions. But again, if you paid attention to everything we learned so far, you should be good. So for the homework of our last class for chapter 3, I have divided it into chapter 3.4 and chapter 3.5. I've decided I'm not going to show you the questions because they're actually really simple. They're just application questions for chapter 3.5. And chapter 3.4 is testing your ability to constantly apply the rules of how to solve an inequality or equation. It'll simply just ask you like, solve this question, and then you'll be like, yeah dude, I'll do it, and then you're all good. For the inequalities, you have really simple ones. For example, like x over x plus 1 is greater than 3. Again, just apply the steps we've learned and then multiply everything by the lowest common denominator. Watch the video. It's genuinely like one of the hardest things you could do here. Everything else will be a little bit more simple. With that in mind, thank you for listening to chapter 3. Next class we'll be going into chapter 4, which will actually start a new unit for trigonometry. So we're going to start learning once again about the sine, cosine, and tangent curves and their graphs, as well as you'll be learning a completely new concept of radians. So that should be a lot of fun. I can't wait to cheat sheet that, but overall, thank you for listening. I hope you've learned a lot from this course.